Hello, good evening. Welcome to today's session. This is the third week of the problem solving session. And today we'll be doing some problems related to the second week and the third week classes, and also the fourth week classes. Majorly, we'll be focusing on the fourth week classes. Kiran, am I audible?
Yes, ma'am.
Okay,
Good
okay.
evening.
Good evening, Kiran. So yes, we'll be going through the fourth week's problems, because that's the assignment I believe that you need to submit. Uh, I think sooner. I think all the 3 weeks assignments have been submitted, right, Kiran?
Yes, ma'am. Yes, ma'am.
Yeah. So you have the fourth week's assignment to submit right now. So we'll focus on the fourth week's problems, as well as a few from the second week and third week also. So I think we'll wait for a minute or two if there's more people to join. Hi, Sati Babu.
Good evening, ma'am.
Good evening. So I was just briefing about what our session will be about today. We'll be doing some problems related to your assignment in the based on the fourth week's lectures. And also we'll be doing few problems related to the second week and third week. Okay, so then we'll start with the session. So welcome to all of you who's joined the meet today. So we'll move on to the question discussions for this week. This week's lecture was basically on storage structures for raw water storage and treated water storage. How is their design? Where is their appropriate location? What are certain considerations done when they're designed? And majorly based on all of that. So we'll move on to today's question session. So like I've been saying in the last few weeks, we'll make this an interactive session, so it will be interesting for me as well as for you guys. So you can just give me the answer in the chat box for the questions, and then after that we'll move on to the discussion of the solution or the answer. So this is the first question. Large impounding reservoirs are typically provided for storage of treated water within the distribution network? Is it for storage of treated water after treatment and before distribution? Or is it for storage of raw water between intake and treatment plant, or storage of raw water before the intake? Karen has answered it as so. Here itself, from these answers, we can see that there are two types of storages happening. One is storage for treated water, and another is storage for raw water. So that is two categories that we'll be looking into. And again, the next point to be looked at upon here is, where is the placement of this storage reservoir within the distribution network, after treatment, before distribution network, between intake. So this is specifically on the location of this storage structure. So Kiran has said it's C, it's D,
Yeah, D finally.
D, okay. Ravi has opted for an option A. Is there anyone else here? Sati Babu and Kaleen, Vijay, you can also just guess the answer if you. Okay, Sati Babu has said it's C. Okay, then we'll move on to the answer. So before moving on to the solution, like I said, storage of water is taking place for both raw water as well as treated water. So even apart from that, storage is something that has to be done at various stages in the water supply system. So here there are three options where they say you can have a storage structure before the intake, storage structure after the intake and before the treatment plant, and storage structure after the treatment plant. That is basically storage before the intake is happening, when the water is needed to be stored because of low and inconsistent flow. So we need to tap that water to provide the water to the system, or to at the point of demand in a regular and regularized manner. So for that purpose, we construct a storage facility just before the intake. So a dam or an impounding reservoir. The question here is about large impounding reservoir. So a dam or an impounding reservoir is provided where before the intake, in order to tap water streams with low and inconsistent flow. The other two options, when is a storage provided after the intake, it is provided to provide consistent supply of water to the treatment plant. Again, this is because of the inconsistent and low flow. If the water is not being provided at a consistent rate into the treatment plant, again, it is going to be an issue with the treatment plant also. And then for that purpose, we are setting up a storage structure before the treatment plant. Now, there is also storage structure that is provided after the treatment plant, so that you can sufficiently store the treated water and provide it as per the requirements of the consumer. So what we looked at upon here is two factors. One is we need storage structures for the raw water as well as for the treated water. Storage for the raw water is taking place before the intake and after the intake, and storage for the treatment plant is treated water is taking place after the treatment plant. So the answer here is storage of raw water before the intake. So this was the first question. Moving on to the second question. Which of the following is not an environmental impact of the construction of dams and blockage of natural reservoir? Is it high initial investment, destruction of wildlife and vegetation, changes in groundwater profile, rehabilitation of indigenous population? Which is not an environmental impact? This seems like a pretty generic type of question. I mean, we can see from the option itself. Okay, Kiran has said A and D both. To some extent, that makes sense. Sati Babu has said D. Okay, Vijay has also said D. Is there any more of answers anyone would like to? Okay, there doesn't seem anyone answering more. So most of you have said it's D. Kiran has also said it's A. Now, if you look at the raw water storage over here, there's a slide in this raw water storage that is discussing about the environmental impacts One of the environmental impact is resettlement and rehabilitation. Now we might say it's not an environmental impact. Again, here they are mentioning about the indigenous population. Indigenous population is something that is belonging to the belonging as a native to that environment. So again, rehabilitation of indigenous population might not be referring to just human population. It can be to whatever is living in that habitat. So moving that native population of whatever organisms or animals or humans from that is also coming under an environmental impact. There again, the heritage features are lost, local flora and fauna are lost, local water quality is lost, and groundwater regimes are lost. So the question was, what is not an environmental impact? High initial investment is a consequence of making a reservoir, but it is not an environmental impact. So the answer here is A. Construction impacts are on destruction of wildlife and vegetation. Rehabilitation of indigenous population is also an impact of the environmental impact that is arising as a result of construction of dams. And all. So the answer for this question is A. And I can understand why the option D came up. It is probably because we believe the environmental, we can see the population term is only referring to us. It might also mean population of, if a tribal community is existing in an area, then relocating them who are native to that place is also an environmental impact, is what they say over here. It makes sense. Again, at your point of view also it makes sense. But then the most probable option here is high initial investment, which is clearly not an environmental impact. So it would be better to go for a very clear-cut option rather than ambiguous option. Now moving on to the third question. Common preventive measures to control reservoir sedimentation are: is it desilting and dredging, mechanical excavation, upstream afforestation and sediment trapping, or is it all of the above? Hi, Sangamitra. Okay, Sangamitra has said D. Kiran has said D. Any more of your answers? Sati is also saying it's D. Kiran said it's C. Vijay is also saying it's C. Pretty much every one of you have responded to it. So, okay, moving on to the answer. Reservoir, when constructed, there are some consequences that will happen, and one of that problem arising due to in a reservoir is sedimentation. Now, two things can be done when sedimentation occurs. It can either be prevented, or in case it occurs, it has already occurred, it can be removed. So here they have asked the most common preventive measures. So you can see over here, there are two types of measures that can be done with. One is preventing measures, that is preventing sedimentation from occurring. The other is remedial measure, which is dealing with the sedimentation after it has occurred. So few of the preventing measures suggested over here is afforestation and upstream tapping of this reservoir by building check dams. So check dams, or dams called debris dams, will block all the debris and fine silt that is flowing through the river before it reaches the reservoir. So helping the reservoir to not get sedimented. And in case it is occurring, it has already occurred, the remedial measure is to desilt and dredge the reservoir. So here, in all the options over here, you can see desilting and dredging and mechanical excavations are two remedial measures that could be taken to remove, if the sedimentation has already occurred in the reservoir, in order to remove the sediments from the bottom of the reservoir, two methods that can be executed are desilting and dredging and mechanical excavation. Before the sedimentation can occur, preventing one of the preventing measures is to build more not build more, to plant more trees, the process of afforestation, and building check dams or debris dams to trap sediments. That is one of the common preventing measures that are being undertaken. So for this question, option C is the answer. You can refer to slide 10. That is what is this slide all about. Reservoir sedimentation and control. Moving on to the fourth question. Treated water storage facilities are provided in water supply system. Why are they provided? Is it to meet the peak flow demands, to equalize network pressures, to provide emergency water supply, or is it for all of the above mentioned reasons? Sangamitra and Vijay said D. Kiran, what is your answer? Kiran is also saying it's D. Sati Babu also says some answer. Okay, Sati Babu is not saying any answer. So okay, so we'll move on to the solution. So as you can see here, the question here is talking about storage facilities for treated water. Now, why are we providing storage facilities for treated water? And this is mainly to take care of three aspects. One is to provide provide water in the required pressure so that water can be regularly provided with a good value of pressure. Second one is to meet the demand requirement. Storage facilities are considered so that whatever requirement is there, it has to meet the requirement, particularly at the peak time. And third is to provide for emergency water supply. That would be for firefighting. So here, the options were covering all three of the main reasons why storage facilities are provided for treated water. First is to meet the peak flow demand. Second is to provide the water at an appropriate pressure level. And third is to provide water for emergencies purposes. Emergency purposes include firefighting. And then in distribution pipelines, again, if pressure is not maintained, it is going to be difficult. It is going to be bad for the distribution network also. When air is trapped, it is going to deteriorate the quality of distribution pipelines and everything. So, and not only that, if we can provide the water at a particular pressure, then accordingly we can design the distribution pipelines with a smaller or larger diameter. That is going to again reduce the cost of setting up the distribution network. The distribution network is something that consumes the majority of the funds that is required for water supply system. So the cost that is incurred on a distribution network can be reduced by reducing the pipe sizes if a proper standardized water is provided at a standardized pressure, and the storage facilities for treated water will help in that. And not only that, in case of pump failures or there is an electrical failure happening, then at peak flow periods, water has to be provided, and storing it in an appropriate facility will help for that. So these are three main reasons why storage for treated water is provided. So the answer here is all of the above. Moving on to the fifth question. Match the types. They have three types of reservoirs are provided. Which is the most appropriate answer fitting into these three types of reservoir? Okay, Vijay has said it's D. That's it. I mean, Vijay is only given the answer. Okay, maybe this one would have been more clear if I believe if you go through the lectures, there's a clear description for what kind of reservoirs are provided at what stage of the supply system. So let's go on to the explanation. So there are three types of storage reservoirs based on the location and function. So you can see the So here you can see the source of this diagram over here, the source of the water. Then there's an intake pump, intake structure, and immediately after the intake structure, there's one reservoir, a storage structure called the clear water reservoir. Now, why is this clear water reservoir provided? It is used to store the treated water at the water treatment plant before pumping into distribution. So this clear water reservoir is stored after the intake structure, before the service reservoir, before pumping it into the distribution network in order to store the treated water, maybe like how we had discussed, so that appropriate it can be provided in an appropriate pressure and to meet the peak value demand. Now, distribution or service reservoir is provided at the center of the demand point. That is, you can see here, this is the location where the demand consumer end, and this is the service reservoir. The service reservoir is exactly at the center of the center, which means that it is between the source of the water intake and the dip point of demand. So distribution service reservoirs are also provided so that water can be given at a particular height, a particular head it can be provided. The required head the point of demand requires. So service reservoirs or distribution reservoirs are placed at the center of the network, and intermediate tank or a balancing reservoir is provided after the service reservoir, somewhere in between the point of demand and the service reservoir, distribution reservoir, for storing water during low demands and supply during peak demands. That is when demand of the water is low, the water can be stored over here. And suppose the supply of the water is the reservoir is not able to provide water at a high demand period, then the water from this storage reservoir, which is a intermediate tank or a balanced reservoir, can be used. So these are the three types of reservoirs based on the location and function. OHSR at center. May I know what is OHSR, Vijay? Okay, I didn't understand what you meant by OHSR. So this is the way in which the reservoirs are placed. First, after the intake, or nearest to the source, we have a clear water reservoir. We have a distribution reservoir, overhead service reservoir. Okay, this overhead service reservoir is for at the center. This can be called as an overhead service reservoir also. Mainly, it is given at the center of the whatever reservoir is provided at a particular, that can provide water at a particular height, like an inch tank, or like you said, overhead reservoir. That is in the center of the demand point, which means the center point from the source and the demand point. Before that, one reservoir is provided, that is called the clear water reservoir, and after the distribution reservoir, whatever reservoir is provided is called the balancing reservoir. And these are the functions of all these reservoirs. So in our question here, clear water reservoir is located before the distribution network to store treated water before pumping. Service reservoir is located at the center of the distribution, and C, balancing reservoir is within the distribution network for storing water at low demands and supply during peak demand. So it will become A2, B3 and C1, which is option D. I hope this answer is clear to all of you. You can refer to slide 17 and the diagram, which is particularly will be helpful in remembering where and all these reservoirs are located. Okay, so moving on to the next question. The effective volume in a service reservoir is denoted by the equalizing storage plus the emergency storage, or is it the operational storage plus the equalizing storage, or is it the emergency storage plus the operational storage, or is it none of the above mentioned answers? We got Mujahid saying it's B, Kiran saying it's A, Vijay saying it's C, Sati saying it's B, Ravi saying it's C. So we have got all the answers, I believe. A, B, C. Is there someone saying D? Okay, don't say D. Okay, Mujahid has said C now. Okay, I'm sorry. I was not supposed to give the answer, but I gave it. Okay, so before we go into that answer, let's take a look at what are the different kinds of storages. So if this is the reservoir, there are four categorization of storages basically. First, the topmost storage is named as the operational system or operational storage. The second one is called the equalizing storage. Third one is called the emergency or fire storage, and the fourth one is called the dead storage. Now, what are all these storages? So, what are why are they categorized into the so-called names? So, operating storage is by definition the difference in the volume between the pump on and the pump off level when the tank is normally being used. Now, what is pump off level and pump on level? Pump on level is this level when the pump will be switched on for filling in water into the tank. So basically, you can see that this difference between the pump on and pump off or the operational storage is the actual level of water that is being used for supply. So when water reaches this pump on level, the pump will be on, and when the water reaches this pump off level, the pump will be switched off, and this amount of water is actually being consistently used for supplying to the point of demand. Now, below that, there is the storage amount called the equalizing storage. This equalizing storage is provided when there's high demand of water, like there's a standard average daily demand of water that is consistently being provided. Suppose the demand of water for a particular period of time is increasing. So usually the water that is available in the operational storage will be enough to meet the demand requirement of the population. But say due to certain activities, like suppose there's a festival happening, or there's some kind of fair or some kind of congregating event happening, then the demand for water for that particular period would be high. So in such cases, this storage is going to provide for the water requirement of high peak times. Now, the emergency or fire storage is a storage requirement that is meeting the necessity when there's a fire or there's an emergency requirement where water is required. So this amount of water, the tank is designed in such a way that this much amount of water is set for these firefighting or whatever purposes. Now, before that, there's a contingency storage also, which is not shown here. The purpose of this is to provide when there's a, again, same thing like equalizing storage only, when there's a more higher demands, then there's an in-between storage called the contingency storage. The last storage is the dead storage, which is the bottom zone of the reservoir, where majorly this water is not going to be used, and it cannot be drawn out or used beneficially because the elevation, the water level is at a very low level. So effective storage is the operational system storage, and the wait, equalizing storage plus the emergency storage is called the effective volume of the service reservoir. So if you see over here, by definition, effective volume of the storage reservoir is equal to the equalizing storage plus the fire storage. When I thought it would be all three of them together, but here they've shown that the effective volume means, or by definition, it is equal to equalizing storage plus the emergency storage. So the answer for this will be option A. Effective volume of a service reservoir is the sum total of the equalizing storage and emergency storage. By definition, that might be it. So the answer for this is option A. And this thing is an important question that just usually generally asked. What kind of storage is meeting the requirement for firefighting purposes, and what storage is never used? It's called the dead storage. So this particular part may be something that you would want to focus on more. Now moving on to the 7th question. Difference in volume between the pump on and the pump off levels in a service reservoir is termed as. We just now looked at the explanations of the question. So I believe everyone will know it well. Yes, Kiran has said D, Sangamitra has said D. Yes, I don't think so. We need to spend a lot of time over here. We already did the explanation for what is an operating storage. It is the difference in the level between the pump on and the pump off point levels in the service reservoir. Effective storage is equalizing storage plus emergency storage, Vijay. Now here we are talking about what is the difference in volume between the pump on and pump off level. Pump on level is the level when the pump has to be switched on so that you can pump more water into it. And pump off level is the level at which the pumping will be stopped because the tank has met its highest level requirement. Okay, so next moving on to the 8th question. Baffle valves are installed in storage reservoirs to promote plug flow and maintain water quality, increase the stored waterage, promote the decay of disinfectant residuals, or to support the growth of disinfectant byproducts. Okay, Mujahid has said A. Kiran also said A. Vijay had said it C. So here we are talking about baffle valves in storage reservoirs. Moving on to the answer. Now, water quality in reservoir may deteriorate when it is kept in the reservoir for a long period of time. And why is this deterioration happening is when water is stored in a reservoir, what they do is the last stage of the treatment process is disinfection. So for the purpose of disinfection, mainly most of the time they do chlorination. So generally chlorination is done. So when chlorination is done, they always add an extra amount of chlorine to meet the disinfection requirement that need to occur for a future time. Again, if the water is existing in the tank for more than we are always giving giving a design, when you're designing the tank, we'll always say, okay, for this much period of water, the water is going to stay. We are providing chlorine to meet the disinfection requirement for a future period. But even beyond that, if the water remains, what happens is the disinfectants are going to get used up and it is going to deteriorate. No disinfectant is going to be there. And not only that, this disinfectants, if in case it is exposed to sun or something, they will react to form certain byproducts of the byproducts, which is again going to reduce the water quality of the reservoirs. And also this water is going to get stagnant and it is again reducing the quality of water. So in order to maintain the quality of water, what has to be done is, when the reservoir is constructed, we have to provide the inlet and outlet in such a way that the pumping rate or the pumping will actually help in circulating the water in the reservoir. So when water is circulated, it will prevent the water from stagnating. So there's just not one portion of the water is not the water that is always being used. Instead, all of the water will be circulated within the tank, because the inlet and the outlet are provided at different levels. Suppose the inlet and the outlet are provided at the same level, what will happen is water will come here and the top layer of water itself will be pumped out. And since the rate also will be the same, there's no much movement of water that will happen. Stratification will occur. The top water itself, the fresh water that is coming itself, will be also taken out of the tank. So for that purpose, we have to, you can keep the outlet at a lower point and inlet at a higher point, or change the levels of this inlet outlet positioning. Second thing what we can do is providing baffle. So I think you understand what baffle is. Baffle is like these half walls that are provided. I don't know if I can write. Yeah, so baffle is like these things. If this is the tank, then baffles are stuffs like this that are provided intermediately. So water can come like this, then go like this and go like this. So again here water, it's not just one portion of the water that is being used. All the water, first the water that is entering will move through here, and it will go down. Again the next batch of water that is put will also will get a chance to move. There's again no stratification occurring due to installation of baffles. And plug flow means when one batch of water will go and behind that another batch of water will go. That kind of a process is called the plug flow. Then you can do some management techniques for the operational of this tank, and do modeling. While designing, you can design it in such a way using modeling techniques to by taking care of not deteriorating the water qualities in reservoir if it is made to stand for a longer storage durations. So these are the remedial measures taken to make water not less of its quality. So the answer here is baffle walls are created to promote plug flow and maintain water quality. Okay. Now moving on to the next question, question number 9. Which of the following statements are true regarding the location and capacity of storage reservoirs? A storage reservoir may function as a pressure reducing device in the distribution network if it is located at the center of demand of the service region. The balancing capacity of a storage reservoir mainly depends on the daily rate of pumping, daily demand variation and supply hours. Reservoir capacity is larger for systems with intermittent supply than for systems with a continuous supply. I think this portion comes with the design considerations. I believe design consideration for one type of reservoir. Sangamitra says it's C, that statements 1 and 2 are correct. Kiran is also saying C. Okay, I don't see much answers coming, so I'll move on to the explanation. So here the statements 2 and 3 are true. Why? We'll see. So if you look at over here, there are 3 ways in which we can locate the reservoir. One is at the highest point. Another is at the center of the point of demand, which is the center from the source to the city. And third is below the impounded reservoir, that is below a high level reservoir. So why are and what situations do we locate this storage reservoirs? So service apart from the center, storage reservoirs may be placed to alternate location based on the geography. So when you're locating a storage reservoir at a high point, what is happening is, although it is very far from the city, because of the elevation of this point where this reservoir is located, an appropriate head can be obtained to provide water at a good amount of pressure. So when you are getting a good amount of pressure head over here, even if it is very far from the point of demand, because of the potential energy that will be there because of the elevation of the location, we can provide a reservoir at the highest point of the reservoir. So based on the geographical requirement also, the reservoir can be located. Usually it is located at the center between the source and the city. That is a normal type of storage reservoirs that we discussed about earlier. Now again, in hilly areas, when the water source is at a very high level, you can have an impounding reservoir. This is a water source at a very high level, and we can provide a storage reservoir at the downstream of this impounded reservoir. Why? To reduce the pressure, because to standardize the pressure, because at this high level, if water is directly provided to the point of demand, maybe the pressure will be very high. So in order to control the pressure, like a pressure reducing device, this reservoir can be located below at the downstream of an impounded reservoir, which is at a high point. When the source of water is at a high point, at the downstream you can locate a reservoir just to control the pressure that is coming. And so these are the 3 categories based on the location of the storage reservoirs. Storage reservoirs in the usual case can be provided at the center of demand. Secondly, it can be provided at a location which is at higher elevation. Thirdly, it can be provided at the downstream of a high level source. So these 3 conditions are what we are talking about over here. So that is why you can see the option here. Option here, they're talking a storage reservoir may function as a pressure reducing device if it is located at the center of demand, which is not true. A storage reservoir will act as a pressure reducing device when it is located at the downstream of a high level source. And the source of water is at a high level, the storage reservoir will be located below that, so that it can act as a pressure reducing device. The remaining 2 points are correct. It is provided mainly for daily rate of pumping, daily demand variation, and suppliers. Normally what a storage reservoir done is that. And reservoir capacity, okay, we didn't talk about the capacity, we just looked at the location. Now what should be the capacity of the storage reservoirs? So storage reservoirs should be the capacity of storage reservoirs should be done for based on the rates of pumping, the pumping system that is set up, and what is the rate of pumping, the daily variations in demand. So an analysis of how the demand is applying, and also the hours of supply, based on the what all hours the water is being supplied, should be the basis for the deciding the capacity of the storage reservoirs. So here the answer for this would be statement 2 and 3. Reservoir capacity is typically larger for systems with intermittent supply, because in continuous supply we are not there is a consistent supply of water, but in intermittent system we have to store the water, so the reservoir capacity will have to be larger. Usually it is 25 to 35% is the quantity of water to be supplied in May if it is a continuous supply. And in case of our intermittent supply, the capacity will need to be more than that of a continuous supply. So these three are the points being discussed in this question. One is based on the location, the other two is based on the how we have to decide the capacity of a storage reservoir. For intermittent supply, it is large. For continuous supply, it is 25 to 35% of the water quantity that is being provided, and it has to be decided based on the rate of pumping, the pumping system that is being set. What is the variations in the daily demand, and also when the water is being supplied, what all hours the water is being supplied. Now moving on to the 10th question. The maximum permissible limit of the total water level drop in a concrete service reservoir over 7 days testing period is. Okay, this you might need to go through the lectures in detail, because this is the test and these are some parameters relating to the test. So yeah, Mujahid said it's D. And hopefully if you have gone through all the lectures, this is one test that is deciding the limit of total water level drop in a concrete service reservoir. Let's move on to the answer. So here you can see this is the test for a concrete reservoir. It should be left to stand for 3 to 7 days for the concrete to absorb the water, more like a curing process. And then in the next 7 days, the total drop in the water level should not exceed beyond 1/5 the average water depth after deducting any measured leakages through walls and making allowances for evaporation or condensation. So what is the permissible limit? 3 to 7 days it has to be let to stand in the water, and in the next 7 days the water should not drop to 1/500 of the average water depth after all the leakages and allowance for evaporation has been considered. So the answer here would be equal to 1/5 of the average water depth. You can see here 3 to 7 days. In the next 7 days it should not reduce to 1/5 of the average water depth, the drop in the water level. So this is the test for water tightness of a concrete reservoir. So it would be useful to go through this once, and this point looks like one of the important points that has to be kept in mind. Again, if the test is failing, there has to be some leakage reasons, and measures have to be taken to identify the point of leakage. Okay, so moving on to the next question. The hydrograph method of estimating the capacity of service reservoirs. So there are various methods to decide to estimate the capacity of reservoirs. One method is the hydrograph method, the mass curve method, and another method is this balancing storage method. So in the hydrograph method, what is the y-axis and what is the x-axis is the question over here. Majorly, what is the y-axis? They have said hours of the days in the x-axis. What is the y-axis? Mujahid has said B, Kiran has said C, Mujahid has again said B. Okay, I don't see much answers coming. So moving on to the solution. Now estimating reservoir capacity, the hydrograph method, how I'll just briefly explain how it is done. So in the hydrograph method, what is happening is a hydrograph, that is time versus demand is being made, and the demand over here is the hourly water demand on a maximum day. We had computed the maximum daily demand as 1.8 into the average. So hourly water demand on a maximum date is the one that is plotted in the y-axis. The corresponding time is plotted in the x-axis, and this curve is the curve for the required storage. That hydrograph is giving us this curve. Now, how can this be used for determining the capacity of the reservoir? Is first is after plotting this hydrograph curve, which is depicting the required storage. It is total storage. No, sorry, depicting the demand, whole demand of that place. We are also going to plot the value of the supply curve. That is, what is the pumping rate that is possible available in that area. So water is going to be pumped at this rate, P value, P to Q. This value it is going to be pumped, but the water demand over here is following this hydrograph. So whatever water volume that is coming under this pumping rate will be fulfilled, but whatever value, that is whatever hydrograph value that is coming above this pumping line will have to be provided as an extra storage. This is how the hydrograph is interpreted. So you can see here for 24 hours pumping, constant pumping rate is also plotted. This constant pumping rate is the rate at which the water is going to be supplied. So that pumping rate will only provide for this much of water that is coming under this curve. The remaining water will have to be provided by providing an extra storage, because only then the whole of this demand will be taken care of. So this is how reservoir capacity is estimated using the hydrograph method. Now in the coming problems, there's one balancing storage method also. That also we'll look into it, how it is done for estimating the reservoir capacity. So here the answer would be hourly water demand on a maximum day. I think this you need to remember, because I don't see any maximum daily demand is not anyway. It's a cumulative value. Whenever mass curve is being plotted, it is always a cumulative value of the demand. So hourly demand on a maximum day is what is going to be plotted in the y-axis, and the time is going to be the value in the x-axis. Hydrograph is always having the rate versus time. You can see the unit over here is liters per hour. It is the rate of flow of water, rate value that is being plotted in the y-axis, and that to hourly water demand on a maximum day. So we'll go into a problem. I'll give you a few minutes into reading this problem, understanding it, and trying to solve it yourself, because I believe this is the only kind of problem that can come out in here. So I'll give you two minutes to just go through the problem and solve it. A service reservoir is constructed to provide a buffer storage, that is an extra storage for 150 days. The population of the town is given. The per capita demand is also given. If the effective storage is 75% of the total volume, the depth of 9 meters is maintained. What is the optimum area of the service reservoir? Is anyone of you trying to solve the problems? Because I hope you're doing. Okay. Mujahid, were you able to get an answer? Okay, you say it's B. Shall I move to the solution part, or does anyone need more time to try solving it? Okay, I think I'll go on to the answer. So here's how it is being solved. The storage required, you can obtain the storage required by multiplying the population with the liters per capita per day demand. So when you do multiply the population, you can know for the entire population what is the amount of water required. Now when you multiply that with the number of days, we can get the volume of the water that is required. Here, since the volume of the water required is in liter, we have to take care to convert it to meter cube. So the storage in volume obtained will be 5.063 into 10 to the power 5. I hope you understood this part. First, what we have to do is we have to get a volume value. Volume value can be obtained by multiplying the population with the average demand in liters per capita per day, which will give us the liter per day rate. That when we multiply it with 150 days, we will get the liter value. That when you convert it to meter cube, you will get 5.063 into 10 to the power 5 meter cube. Now they have said the effective storage is 75% of the total volume. So what does it mean? We have got whatever storage that we have got here is the effective storage. So that effective storage is going to be 75% of the total volume is what they are saying. So in order to get the total volume required, we divide this effective storage by the the value that is given, 75% of the total volume. So the effective storage here is the 75% of the total volume. So when you divide the effective storage by the 75%, you will get the total volume that is required, which is 6.75 into 10 to the power 5 meter cube. Now they have given a permissible depth of 9 meters maintained. So when you divide this volume by the depth, you will get the optimal area required for the service reservoir, which, like how Mujahid said, the correct answer is 7.5 into 10 to the power 4 meters square. I'll give you some more time to go through this solution. You want to take it down? The slides are available. You can go through it. So in order to calculate the storage, first we multiply the population with the average demand and multiply the whole thing again with the number of days. You will get a value in liters. Convert that liter value to meter cube.
Excuse me, what is the exact meaning of buffer storage?
Buffer storage is the extra storage that is required. when you say that we talked about uh, the hydrograph method, right? So in that they are saying that the required storage is after calculating the demand and the supply. So for that purpose only we have to calculate the storage demand. That is for 150 days. It is requirement is what we have calculated over here, the effective storage. So when we calculate the effective value that is provided, that is for 150 days, whatever storage value that we have received is this value in volume, in terms of volume. When you're dividing it by a 75%, that is out of the total volume, this buffer storage took 75% of the value. So when you divide by the 75%, you're getting the total volume that is actually required to be total volume of the reservoir that has to be provided. And in that there is a 9-meter permissible depth. So when you do the divide the volume by the 9-meter permissible depth, you can get the area that is required for the service reservoir. This is again a design consideration, part of the design process. Now we'll move on to some more some estimation problems. Here they have again provided an elevated service reservoir with the values: population 25,000, average daily demand is 135 liters per capita per day, and water is pumped from 8 a.m. to 11 a.m. Like we had discussed earlier, we had to take care of the capacity of the reservoir in such a way that it is meeting the it is taking into consideration the hours of the supply also. So here they are saying from 8 a.m. to 11 a.m. water is to be pumped, and the variation in the daily demand is provided in this table. That is from 12 to 6, 10% of the total demand is required. 6 to 9, 35% of the total demand is required. That makes sense because 6 to 9 is the time when people are getting ready for the office and school. So that is the time when more water is required. 9, 12, 20% of the total demand, and so on and so forth until 24 hours. What is the total demand based on the certain times of the day? Now here we are supposed to be providing water from 8 a.m. to 11 a.m. Based on the data provided, first you have to find out the cumulative daily demand for the city in million liters per day. So again, since it is coming in the unit million liters per day, you can understand you have to multiply some value with the population, right? So if you multiply this population value with the average daily demand, you will get the cumulative daily demand. Then next question they are asking is the hourly pumping rate for a uniform pumping between 8 to 11 a.m. Here they have provided okay, they want the pumping rate, what is being provided. So that can be obtained. Pumping rate means it's liters per hour. So we can obtain that from by knowing the number of hours. That is from 8 to 11, it is 9, 10, 11, 3 hours. If you divide if you convert this value into an hourly value, we will get the answer for the 14th question. 15th one is using the balancing storage method that I told I'll explain. 3.37 million liters. Yes, is this the 13th answer, right? I believe so, yes. Okay, can you try finding the 14th one also? Here we got the million liters per day. So what is the million liters per hour? Hi Kiran, Sangamitra, are you doing or do you want me to go on with the solution? Okay, so let's see the solution. So total water requirement, like you said, is 3.37 million liters per day. Pumping hours 8 a.m. to 11 a.m. is 3 hours. So hourly pumping hours will be 3.375 divided by 3. So 1.125 million liters in 1 hour. When you talk about million liters per day, for whole day, this is the whole volume of water required. In 1 hour, this is the volume of water that has to be provided. Now, oh, you okay? Mujahid was still doing. I'm sorry, I didn't see your answer. I just went on to the. Okay, Mujahid, are you still doing? Okay. So now you can see over here, they had given us certain percentage of the total demand for particular hours of the day. And based on that, we got the total water requirement. Total demand is 3.37. So 10% of 3.37 is going to give us one value. And this is the demand for this period of time. 0.281. Okay. Okay. We'll look into the answer. Again, from 6 to 9, since 35% is the total demand, 35% of 3.375 is going to give 1.1813. Now here they are asking for the cumulative demand. In the balancing storage method, we are looking at the cumulative demand. So once you get this value, you have to keep adding on this value to the next value that you're getting. And in the end, here you can see that the total demand is what is we are getting, what we are obtaining in the end. Now let's see how we are going to plot the okay, there's a little variation in the answers that you have provided, probably because you're not aware about the balancing storage method. Now if you're not aware about the balancing storage method, let me explain to you how this method is done. So on a graph, we are going to plot the curve, plot two curves. One is the demand curve and one is the supply curve. Now demand curve is going to be these values, that is what is the requirement of the water, the total daily water requirement, and particularly from 12 a.m. to 6 a.m. what is the water requirement, and you have to take care that it has to be the cumulative water demand. So we had got a period 12 to 6 a.m. So some 6 is coming somewhere around here. At 12 a.m. the zero water requirement. At 6 a.m. it is going to be 0.3375. Again 6 a.m. to 9 a.m. it is going to be 1.5 something. And from 9 a.m. to 12 p.m. it is going to be 2 point something. So this is the demand curve that is being plotted. So after that, they are going to plot the supply curve. So supply has been given for the time 8 to 11. They have told that the pumping is being done, that is the water is being supplied between 8 to 11 a.m. and that also at an hourly pumping rate of 1.125 million liters per hour. Okay, so that curve is provided as this orange line. So you can see at 8 a.m. it is 0, at 9 a.m. per hour it is 1. What was the value? 1.125. So 1.125 is the value at 9 a.m. Again 1.125 plus 1.125, that is coming to around 2.25 will be the value at 10 a.m. and at 11 a.m. it will become 3 times 1.125. So this is the supply curve. I hope everyone is with me in this way, how the this curve is being plotted. First we'll plot the demand curve, then we'll plot the supply curve. Now the third step is to find the maximum ordinate between the demand and the supply curve. That is, here you can see the maximum distance that is coming between the demand and the supply curve is the value over here from this point to this point. And again the maximum second value, that is maximum supply, excess of supply that is coming, will be from this point to this point. Whatever is coming under is the maximum excess demand coming, and whatever coming above is the maximum excess of supply coming. So these two values are calculated. Now these two values, after being calculated, is added to get the balancing storage. Like we had again, if you take the hydrograph method, we had plotted the pumping rate, we had plotted the hydrograph, and whatever water is not being covered by the covered under the pumping line is being given as the balancing storage. Balancing storage is to compensate for the water that cannot be supply that cannot be supply, that is not matching with the supply is not matching with the demand. The whatever storage has to be provided excessively is what is called the balancing storage. So here, through the balancing storage method, this is how we do the calculation and get the answer. You can actually wait a second. I can show you the slide which is taking into consideration this. Folders. Yeah, so if you can see here, they have told how the method is being used. First, a mass curve is plotted of accumulated supply through pumping or demand versus time. So for one period of time, there will be one demand and supply. This is the demand curve, that is from 12 a.m. to 5 a.m. there would be one value. Then from 5 a.m. to 8 a.m. there would be one value. So when you plot, you will get a graph like this. Then the supply curve is going to be a uniform rate curve, that is also plotted. Then what is the maximum distance between this demand and supply in below the supply line, and what is the maximum distance between the demand and supply above the supply line? Two values are obtained, and by adding both those values, you can understand what is the balancing storage that is required. So please refer to the slide for a more better understanding of yeah, so better understanding of the method. And I'll also be providing the the PPTs are also going to be uploaded, so you will be able to see into this. Now we will move on to some questions from water demand and aquifers, which were discussed in the previous sessions. So here there is one sample problem that is making use of the arithmetic regression method. You can solve it for revising these portions. So if we keep revising these portions, it will be easier for you to, I mean, it won't be a burden during the end of the session. So I will be always providing some numericals based on the previous sessions also in the coming sessions, so that we don't have a gap between the concept. So this is one problem. Population figures for 4 years are given. You're supposed to find what is the predicted population in 2010 by the arithmetic increase method. Okay, C, Kiran has given C as the answer. These are problems that we had solved in the last class also. And this would help you to keep in touch with the formulas. Mujahid has also said C. Does anyone else have an answer? Let me see. Sangamitra, Sati Babu, Kaleen, do you have an answer? Okay, I'll move on to the solution. So this is, oops. Yeah. Sangamitra also see. So this is how it is solved. You can see the per decade increase in population is calculated. 3 increases are there. We are dividing it by 3 to get the Ka value, or in here it is given as the X bar value. That multiplied by the decade that we require is 2010 is the decade required. So 2010 minus the latest population data by is at 2000. So that divided by 10 will give us the decade value. N is equal to 1. And by this formula, PO plus Ka into N, we will get that 58,000 plus 6,000 into 1 will give us 64,000. So all of you had given the correct answer. Now next question. This, I hope the question is clear. The print is not very clear. Population data pertaining to a community is given below. We are supposed to find the population for the year 2030 by the geometrical increase method. Year 1 is 1980, 1990, 2000, 2010. 10 years data is given. First population is 40,000, 50,000, 80,000 and 1,40,000. A simple direct substitution of the formula. Okay, I'll move on to the solution. Now we can see 1980, 1990, 2000, 2010. These are the populations. When it comes to geometrical increase method, we calculated by finding the difference between the two population and dividing by the difference and multiplying it by the percentage. So for each value, these are the percentage values you get: 25, 60 and 75. After that, multiply all the three values to the power to the how many number of values are there, to 1 by to that power is what is giving us a Ka value. The number of decades required here is 2 decades. Initial population is 1,40,000. By substituting in this formula, where A value is going to be the decades value, we will get the answer 3,07,795, which is option. Oh, sorry, no option was given. So yeah, it's a direct fill in the blanks question. Moving on to the next question. This is the actual volume of water that can be extracted by the force of gravity from a unit volume of aquifer material is known as. Okay, I'll give you the answer. It is specific yield. So specific yield is a volume of water that can be released by gravitational effect from a unit volume of an aquifer. That is by definition. Yes, correct. Khalil, specific yield. Now again, another question based on the same thing. Volume of water that can be released by gravitation effects from a unit volume of an aquifer. The option is the repetitive question. The answer is again B. Yes, you're right, Kiran. We had just discussed this. So it would be useful to know what are the other terms also. Okay. Yeah, so we would like, let's look into what are the other terms here. Specific yield is a volume of water that can be released by gravitational effects from unit volume of water, unit volume of the aquifer. What is specific storage? Specific storage is the amount of water that a portion of aquifer releases from storage per unit volume per unit change in hydraulic head when it is fully saturated. So specific storage is again when, if you consider a column of the aquifer, and when there's a reduction in hydraulic head by one per unit change, say 1 meter or 1 centimeter square per unit volume of the aquifer, then whatever amount of water that is being released is called as the specific storage. So again, you can see this as specific yield by per unit hydraulic head. Can also, we can also call it that, the definition. What is specific capacity is the discharge per unit drawdown. When 1 meter of drawdown is happening, what is the amount of discharge that is occurring is called the specific capacity. So here it would be good to know the definitions of what is specific storage, specific capacity, specific porosity is, I'm not sure what it is. I'll maybe tell you in the next session. But this is what is the definition for the remaining three options.
I think specific porosity is not there, but only porosity term is there.
Yeah.
Volume of
Porosity,
void by total volume.
yes, right. I don't know if specific porosity is there. Anyways, I'll just look into it. If there's a term like that, then maybe we should discuss it. Anyway, thank you. Thank you. I think it was Sangamitra or Kiran?
Yes,
Sangamitra. Okay. So, thank you, Sangamitra. Now, the relationship among specific yield, specific retention, and porosity. Excuse me. Jahid says it's A. Okay, I thought this would be a very simple question, but yeah, so मुझे Sangamitra and Kaleem has given us the right answer. The relationship between specific yield and specific retention is specific yield plus specific retention is equal to porosity. It is Sy plus Sn is equal to porosity. This is the relationship between specific yield and specific retention, SR, sorry. And so you have to be careful when you see this relation. Specific yield is equal to, so N minus SR. This is going to go there, so it is going to be N minus SR. So be careful about it. Okay. Okay. Now moving on to the next question. A soil formation through which only seepage is possible, being partly permeable and capable of giving insignificant yield, is classified as. So we had seen a few classifications in aquifer, acutard, aquifuge, and acufluid. If you know what the definition of each is, you will be able to answer this. Okay, Kaleem says it's B. Baira says it's B. Okay. So here, if you see, it is correct option, option B. So you see here, what are the definitions? We can look at the definitions of aquifer, acutard, acufluid, and acufluid one by one. Now, aquifer is permeable formations, which is permitting appreciable quantity of water to move through them. Like water can be extracted easily through aquifers. Acutard is when the formation only seepage is possible and yield is insignificant compared to an aquifer. Seepage is happening, but then you cannot extract a lot of amount of water from acutard as compared to that of aquifer. Acufluid is when you're not at all able to extract waters from this formation. An aquifuge is again an acufluid, only thing vertical movement of water is possible. There is some kind of impermeable formation only. So sorry, aquifuge is when you have there is no possibilities of transferring or store. It can never transmit water. Also, you cannot take out water. Also, I'm sorry. Aquifuge is that. Acufluid is when you can actually there might be vertical this one, but then there is the transmitting capacity of water will be significantly less. Okay, again, next is on population. Increase in population of a rapidly growing city may be estimated by. We had talked about how the what kinds of city, whether a rapidly growing city, large city, moderately old city, based on the types of cities, one method is there. Which out of this method is good for in a rapidly growing city? Kaleem says it's 2. And the answer is geometrical method. So here I've made a table with what kind of cities require what kind of prediction method. So in arithmetical increase method, it is applicable for large and established cities, can make use of arithmetical increase method. Geographical increase method is for the places like we just discussed. It's got a good scope for expansion, rapid expansion possibility. Cities with that kind of a scope and new cities the population can be forecasted using geometrical increase method. Incremental increase method is suitable for cities of moderate size and age, and logistic curve method is useful for large cities with varying demographic data. Okay, this is one problem. You can try doing it. I'll give you 2 or 3 minutes for doing this. This is based on the aquifer and drawdown and well hydraulics. So here a volume of groundwater is being pumped out from an unconfined aquifer with an area of 5 kilometers square. The pumping is lowering the water table from 102 meter to 99 meter. What is the specific yield of the aquifer? So we learned that the specific yield of the aquifer is the volume of the water that can be taken out under the influence of gravity per unit volume of the aquifer. They're asking for the specific yield of the aquifer. So we need the volume of water and volume of the aquifer. Since the pumping is lowering the water table of the initial, we have one depth. Mujahid is saying C, Kaleem is saying A. Okay, I'll move on to the answer. So here they have said the water table is being reduced by 3 meters. So volume of the pumped water is going to be, the total volume of the water is 3 into 10 to the power 6 meter cube that they have given over here. Now area of the aquifer given as 5 kilometer square. When you convert it into meter square, it becomes 5 into 10 to the power 6 meter square. So what is the volume of the saturated water? What is the volume of the aquifer water? Will be 5 into the depth of the water that has been reduced. So aquifer is having the water table at 102 meter, which is reduced to 99 meter when the pumping is occurring. So that 3 meter into the area is giving us the volume of the saturated water. Now, how do you calculate the specific yield of the aquifer? Specific yield for volume of the water under influence of gravity for 1 unit volume is SY. Then volume of the pumped water to the total volume of the saturated water through the methods of triangle will give us the specific yield of the aquifer. I think I'll show you how it is done. I believe that is the way. So you can see here, if the specific yield is corresponding to 1 meter cube of water of the aquifer, then for the total water that has been pumped out to the corresponding corresponding volume of the aquifer will give us the specific yield. This is how this question has been done. I think it makes, I don't know if it makes sense to you. This did anyone, I mean, is there anyone who's not able to understand this part? Corresponding value. Specific yield is the volume of the water per unit volume of the aquifer. So SY is the volume of the water that is being flowed out in gravity that is occurring for unit meter cube of the aquifer. Then we know the total volume of the aquifer and what is the amount of water that is being pumped out. From these data, this is how the specific yield will be calculated. Okay, now moving on, next question. For a steady flow to a fully penetrating well in a confined aquifer, the drawdowns at two radial distances are measured as S1 and S2. For a pumping rate Q, no value is given. We just need the formula for the transmissibility of the aquifer. Transmissibility, confined aquifer. What is the formula for the transmissibility of an aquifer? Does anyone have an answer, or shall I move on to the solution? D, 2 pi Q R2 minus R1 by ln S2 minus by S1. Okay. I think you will have to be familiar with the formulas for discharge for an unconfined aquifer and confined aquifer. This will help us in getting us the transmissibility of it. So let's move on to the answer. So as you can see over here, discharge through a confined aquifer is given by this formula, 2 pi kb into h minus h by log of r by r, or also you can write it as h2 minus h1 by r2 by r1. This is by Dupit's formula and this is by Thiem's formula. So this is by Dupit's formula, sorry, Thiem's formula. Okay, so transmissibility is nothing but K into V, the hydraulic conductivity into the thickness of the aquifer. When confined aquifer, you are taking care of the thickness. When it is unconfined aquifer, you have to take care of from the datum to the water table level will be considered over here. So the answer here is you have to just multiply this discharge value. You have to take the denominator here. It will be Q into log of R by R divided by 2 pi by H minus H. That is Q into log of R2 by R1 by 2 pi H2 minus H1. In terms, when you write it in terms of drawdown, it will become the other way around, S1 minus S2. So the answer will be option A. Q log of R2 by R1 divided by 2 pi S1 minus S2. Now, next question. A well of diameter 20 centimeter fully penetrates a confined aquifer. After a long period of pumping rate is given in liters per minute. The drawdown is going to 10 meter. No, drawdown at one distance, R1 10 meter and R2 100 meter becomes 3 meter and 0.5 meter. So here we have the value of the diameter of the well. We have the pumping rate Q. We have R1, R2. We have S1, S2. Situations of drawdown at R1 and R2, S1, S2. Q we have. You're supposed to find the transmissibility of the aquifer. Transmissibility of the aquifer, T is equal to K into B. So if you substitute in this earlier formula that we had provided, that we had discussed earlier, that itself will give us the answer. I give you 2 minutes. If you can do the calculation, it is going to be a revision for you for whatever formula. I can also even show you the formula that we had done. This is for confined aquifer. Q is equal to 2 pi kb into h minus h by log of r by r. That is, if it is, if the infinite radial distance r is taken, h will be the corresponding height of the water table at distance r. And if you're taking S1, S2, this is going to be the value. So corresponding to this, we have been given S1, S2 and R1 and R2. Q is also given. Diameter is given. From diameter, we can actually get the small r value. Okay, let's move to the answer. So like I said, T is equal to Kb is what we have to find. We don't have the thickness, nor do we have the hydraulic conductivity. So we are going to calculate. This is a pumping rate. Q value is given in liters per minute. So liters per minute, we are going to convert it into meter cube per day. That is the value of, that is the unit in which we require Q. Radial distance of observation well 1, R1 is 10, R2 is 100, drawdown is 3, drawdown is 0.5 corresponding to the R2 distance. So the discharge through the well is going to be 2 pi kb into h minus h by log of r by r, or h2 minus h1 by r2 by r1. H2 over when you're finding out the transmissibility, you can just you put in this value 3916.8 divided by 2 pi into 3 minus 0.5, which is the H2 and H1 value. H2 will be 3 and H1 will be 0.5. The log of 100 by 10, which is equal to 574.2 meters square per day. So that option is coming as B option. So this is how this problem is being done. You have to keep in mind this formula. I think that is the only two formulas that is required: the specific retention, specific yield, and the relationship with porosity. And these two formulas are the major formulas that is required, which numericals will come. It is there in the lecture notes. Here you can see by Thiem's equation and Dupuis equation. When Thiem's equation is there, they're considering these two heights over here. So you can see here, if this is a discharge well, another well at R1 distance and R2 distance, the drawdown is the distance that is calculated, the depth that is calculated from the top line, cone of depression to the cone of depression, and H2 is that is being considered from the bottom of the aquifer. So you can actually swap the values. If H2 minus, it is H2 minus H1, when you solve it, you can get it as S1 minus S2. So based on that, the solution is there in the lecture material if you go through it. So substituting in this formula for Kb value is what is going to give us the transmissibility. And this is when it is confined aquifer. When it is unconfined aquifer, this formula is going to change like this. Q is equal to pi k into H2 square minus H1 square by ln of R2 by R1. Here earlier there was a 2 pi k into B, which is the thickness of the confined aquifer. When unconfined aquifer is happening, this whole H is considered as the transmissibility. K into H will give us the transmissibility. So that's it for today's class. If you have any doubt, you can stay back, or we'll end the session today. Somebody had asked about the slides and the videos that I guess all of you might have got a link to which you can access it. So do go through it and practice maximum number of questions you can. If anybody has any doubt, you can ask now.
Would you please repeat question number 10? I could not heard properly due to network problem.
Question number 10, what was the question about? Okay, 1 second. Okay, this is about the testing of the reservoir, right? Is it that, Sangamitra?
Yes, this one.
Yeah. So this one is done for the concrete reservoirs. Is a test done to see what is the total drop of water level, if it is appropriate or not, or whether there is any leakage or vent or not. So for that, what you do is concrete reservoirs, after filling the water, it is let to rest for 3 to 7 days. So because this concrete is absorbing water, some water will anyway reduce. So what is the total drop of water has to be measured, and that drop of water should not exceed 1/500 of the average water depth after detecting any after measuring any leakages and allowance for evaporation and all. After that, whatever depth is being measured should not reduce or should not go beyond this 1/500 of the average water depth that is there in the tank. If it goes beyond that, that means that the test is failing, that concrete reservoir is not fit for storing water. Water tightness is not there. So remedial measures has to be taken to maybe line it or whatever, to give an extra coating or so that the water level doesn't drop because of the leakage to a value that is exceeding this value. Otherwise, what will happen is that because of this reduction in water level, the demand cannot be met at some point. Maybe for a small depth, this might be okay, but when the huge depth of water is gone on the basis of leakage or whatever reason, the demand won't be able, there will be insufficiency in meeting the demand. So the question was maximum permissible limit of total water level drop in a concrete reservoir for 7 days testing period should be equal to D option, 1/500 of the average water depth. You have all the lecture materials also in the with the lectures provided. These presentations are also provided. The videos are also uploaded. So if you have any doubt at a later point also, you can go through all of that. If not, there's a discussion forum also, you can ask doubts in that. Sangamitra, Mujahid, do you have any doubts? If there are no more doubts, then
No.
okay. Then we can, you can leave the meeting if you don't have any doubts or anything else to discuss. Okay, so I'll be winding up the session. Thank you all for joining the session. We'll meet you next Saturday. There's going to be one more session on Tuesday. So yes, thank you all for attending the session. Bye bye and good night.